Good morning, one and all. So, in the last class, we have seen some of the theoretical things for the digital communication techniques. Now, yesterday I told you, so we have a vector called observation vector, or also called as received vector, capital X, which contains n elements, namely x1, x2, so on, so on, xn. Now, we have found out the mean and variances of all these elements, and also we have proved that so all these are independent of each other. Now that's why what I can write is, I can write the conditional PDF of this vector capital X as the product of individual conditional PDFs of these elements. How can I write like that? Because just now I told you they are independent of each other. So this is what the final conditional PDF of the observation vector capital X given Mi. How it is that? It is a product of individual conditional PDF of elements of the vector capital X. Now, so you know already the elements are having some mean and variances, and so from that we can also find out the conditional PDF of those elements, n elements. What are those elements? x1, x2, so on, so on, xn. Now this is the conditional PDF of xj, jth element of the vector capital X given Mi. That is about condition about Mi. Now how is that? Generally this is the formula. This is the generalized PDF of the Gaussian process. 1 by root 2 pi sigma square e power minus of x minus mean whole square by 2 sigma square. Now here we know what is x? X is xj. That is the jth element of the vector capital X. Now what is the mean of xj? Sij whole square by, what is the variance of xj? n0 by 2. The variance is same for all the n elements. I told you yesterday also. Now if you simplify, you will get like this. Now this is the conditional PDF of jth element, only one element. Now so here, now what happens here? Here, so in order to find out the conditional PDF of this vector capital X, we have to multiply n such PDFs, conditional PDFs. So here I have written product j equal to 1 to n, so individual PDFs, which means you have to multiply these n times. Okay, so product j equal to 1 to n, 1 by root pi n naught e power minus of xj minus sij whole square by n naught. Now here, so how to find out this product? So here this is a constant. You are multiplying this how many times? N times. 1 by root pi n naught into 1 by root pi n naught, so on, 1 by root pi n naught. How many times? This is n times. Now, so here, now you know already. So if I say e power a into e power b, it's nothing but, what is that? E power a plus b. Isn't it? You know this simple mathematical formula. Now here, so if I take this product inside the expectation, if I take this inside expectation, it becomes summation. Why? Because so e power a into e power b is nothing but e power a plus b. Here these two are multiplied, here these two are added. In the same way, if I take this product into the expectation, it becomes summation. Now here, so if you multiply 1 by root pi n naught n times, what do you get? 1 by pi n naught whole power n by 2. So you just find out this into e power, the expectation, or e power. Now this product becomes summation. So minus 1 by n naught summation j equal to 1 to n xj minus sij whole square. Now this is what the conditional PDF of capital X given Mi. I hope you are okay with these simple calculations. So you just go through the simple calculations, you will understand very clearly. So it's not a big deal at all. Okay. You just go through it once. So I have done simple calculations. That's it. So nothing to worry. You just multiply this n times by bearing j equal to 1 to n, which means so we are multiplying x1 given Mi, x2 given Mi, x3 given Mi, so on, xn given Mi. What are x1, x2, xn? They are elements of vector capital X. Okay. Now, so this is finally the conditional PDF of x given Mi. So this is one form. pi n naught whole power minus n by 2, or you can also write like this also. Expectation or e power minus 1 by n naught summation j equal to 1 to n xj minus sij whole square. I varies from 1 to m. What are these 1 to m's? They are number of symbols that we are transmitting. Okay. See, always remember I means which symbol is transmitted. J means which element is received. Okay. I varies from 1 to m, j varies from 1 to capital N. Okay. Now, so these are the two forms of the conditional PDF of the observation vector or received vector capital X given mi. Given mi means ith symbol is transmitted. Given that ith symbol is transmitted, so this is a conditional PDF of the particular scenario. Okay. Now, so we know already xj equal to, I told you yesterday also, what is xj equal to? Sij plus wj. Is it okay? Xj equal to Sij plus wj. Now j varies from 1 to m, 1 to n, sorry. Now then what happens? So let us write everything in a mathematical or matrix form. So j varies from 1 to n. Then what happens? Xj equal to Sij plus wj. X1 equal to, mean j equal to 1. X1 equal to Si1 plus w1. Sorry, this should be x2. I'm sorry. X2 equal to Si2 plus w2. So on, so on. Xn equal to Sin plus wn. Now, so if you write everything in the vector form, this forms the what vector? Vector capital X. X1, X2, so on, Xn. It forms the vector capital X. That is also called as observation vector or received vector. Now, what are these elements form? Si1, Si2, Si3, so on, Sin. They form a signal vector Si. This vector is capital X. This is vector Si. And this also forms another vector W. Now, so everything is a vector form. Now, finally, so capital X, vector capital X equal to vector Si plus vector W. Otherwise, you can write like this. Okay. Now, here we got three vectors. What are they? Received signal vector or observation vector. Si is a signal vector. W is a noise vector. Okay. Now I varies from 1 to m. Clear? Now from this formula, I have written everything in the matrix form or in the vector form. I hope you are okay with this. Now, so these are all the some simple nomenclature of the given vectors. Number of basis functions, transmitted signal vector, sorry, it is reversed. Here x is a received signal vector, this is Si is a transmitted signal vector, and this is a noise signal vector. Okay. Here, so we can represent all three vectors in the constellation using points, namely received point, message point, noise. Okay. So this vector can be represented with a point in the signal space diagram. So I told you these things while discussing the constellation diagram of BPSK. There also we have represented a vector with a point on the signal space. Anyway, so I'll take an example. Now, so for time being, we'll discuss this later, but this is also very important, which is written in the box. Okay. Anyway, so as of now, we got three vectors whose order is n cross 1 or n by 1. So they represent received vector, signal vector, and noise vector. So obviously in any communication system we need these three parameters actually. What is transmitted and what is received. Obviously, what is noise generally? Noise is difference between what is received and what is transmitted. Okay, so it is just dependent. So if take what is difference between vector x and vector Si? Vector x, vector x and minus vector Si. This should be what? Noise. So the difference between received signal and transmitted signal is nothing but the noise. If there is no noise, if this is 0, what would happen? X equal to Si, which means so you are receiving same thing as transmission. So whatever is being transmitted, same thing is being received. That is a simple meaning. Okay. If at all there is no noise, isn't it? if there is no noise, what will happen? Both are same, which means so your receiving would be same as your transmitted signals. Okay. Now, so this is what we represent everything geometrically. Now I have taken a three-dimensional constellation or Euclidean space. Now this represents a signal vector Si. It is also called message point. Now this represents observation vector capital X. It is called received signal point. So this is a point. So if you join from origin to this point, you get a vector. Now obviously, what is this? This is a difference between these two. That is nothing but noise vector. Okay. So which means this is, see, you are transmitting this point. Obviously, simple meaning is you are transmitting this point, you are receiving this point. Obviously, this is the difference is noise. If at all suppose if there is no noise, what would happen? These two will coincide. Which means so your transmitted point will same as received point. So that is the ultimate success because there is no noise. Okay. One more thing. If noise is very less, what would happen? What is the conclusion? They will be very close to each other. Isn't it? If noise is less means the distance between these two vectors is less. Which means they are very close to each other. Okay. So simple meaning is if the received vector and the transmitted vectors are very close to each other, which means there is very less noise. So if noise is more means they are very far away from each other. Isn't it? Okay. Anyway, so we'll discuss everything in detail later, but this is a simple geometrical representation of all three vectors and their meanings. Okay. Now, so here, so we have to know something about likelihood functions. Okay. What? Likelihood function. Now here, so here what is the problem now? So here at the receiver, we are given observation vector capital X and we require to estimate Mi. So that is the next task. That is the decoding. So let me go back. So I told you in the starting itself. So in the receiver there are two parts, namely detector followed by decoder. So here, yeah. Now here, so from x of t we got x is a vector. So from vector x you have to get the estimation, which means so from this vector x we have to estimate what is transmitted. Okay, we don't know what is transmitted actually. So we have to estimate what is transmitted, that is called MCAP. So that is done by this decoder. It is called ML decoder. I will explain what is ML means. Okay. Now let us go with the decoding part, the last part of the receiver or second part of the receiver. Okay. Now here, so to find out the decoding, we need to define some likelihood functions. So likelihood function is nothing but conditional PDF only. But so we take log likelihood function, which means we take natural logarithm to that function. So L of Mi equal to natural logarithm of this conditional PDF. So you don't get confused by these things, they are very simple. So you just take the natural logarithm to the conditional PDF. So that is called likelihood function. What is likelihood function? The natural logarithm of conditional PDF of vector capital X. So let me go back. So if you are getting any confusion, simply I am taking a natural logarithm to this term. So that gives you likelihood function. We call it as L of Mi. What is L of Mi? It is simply the natural logarithm of this conditional PDF. You take natural logarithm, what would happen? So this is a constant. Okay, suppose if you take, let us take ln of a into e power b, let us take. A is a constant, e power b. Now what is this generally? Ln of a into e power b. This would be equal to ln of a plus, what is ln of e power b? Simply b. Okay. Now if you take the natural logarithm to this term, you get ln of this term plus only this term. What is term? Minus 1 by n naught summation j equal to 1 to n xj minus sij whole square. I hope you are okay with the simple calculations. Okay. Now, so this is what the likelihood function or log likelihood function. This is what you get. So your e power term will be eliminated. And here I am not writing any constant term. What is a constant term? So let me go back. What is a constant term? ln of 1 by pi n naught to the power of n by 2. It is a constant because it neither depends upon it neither depends upon I and nor j. It just a constant. Okay, it is not a variable now. So that's why we ignore this constant term. What do we write? So ln of this term is same as minus 1 by n naught summation j equal to 1 to n xj minus saj whole square. Just I will write this term, e power term. There is no e power now because it will be eliminated if you take natural logarithm. So I am neglecting the constant term and e power term will be eliminated. So you only take the power of e, that is where you write minus 1 by n naught summation j equal to 1 to n xj minus sij whole square. I varies from 1 to m. Now this is the likelihood function. Okay, so nothing to worry. So likelihood function means take the logarithm of the conditional PDF of x. Okay. Now here we have two types of rules. Okay, namely map rule or ML rule. What is a map rule? It is called maximum a posteriori probability rule. Okay, now here so we have two probabilities. Somewhere I have written a priori probability and a posteriori probability. Okay, you try to understand the definition of these two probabilities. Okay, a priori and a posteriori. Okay, so here this is the simple dictionary meaning of a priori and a posteriori probabilities. Now here, so map rule means maximum a posteriori probability rule. Okay, so I'll explain by taking a simple example. What does map rule mean? Okay, suppose, so consider m equal to 2, binary case. We are transmitting two symbols. Let us take, we are receiving two symbols. Okay, now so let me go back to this diagram first. This is a diagram called binary channel. Okay, we are transmitting m0, m1. We are receiving x0 and x1. Okay, so 2 bits are transmitted, 2 bits are received. Okay, now this is a binary case. Now so this is a simple. Now what happens is, here you can take 4 probabilities. What are they? Probability that x0 given m0. What do you mean by this? Probability that x0 is received when m0 is transmitted. Next, what is this probability? This is a probability. You are transmitting m0 and receiving x0. Okay. Now what another probability? So you are receiving x0 but you are transmitting m1. What is that now? Probability that x0 is received given m1 is transmitted. This is one more probability. In the same way, these are another two probabilities. When x1 is received, m0 can be transmitted. When x1 is received, m1 can be transmitted. Okay. So in this scenario, we have 4 probabilities. What are they? P of x0 given m0, P of x0 given m1, P of x1 given m0, P of x1 given m1. Okay. So these are the 4 probabilities. They are called transitional probabilities or likelihood probabilities. What are they? These are 4 probabilities of the just now explained scenario. What are they? Probability that x0 is received when m0 is transmitted. In the same way, these are all 3 transitional probabilities. Okay. Now, so I want to explain the map rule in the simplistic form. Map rule as well as ML rule in the simplistic form. Okay. Now, so here, what are the a priori probabilities? I told you there are 2 main probabilities, a priori and a posteriori probabilities. What are a priori probabilities? They are P of m1, P of m2, which means, so the probability of transmitting m0 and the probability of transmitting m1. They are called a priori probabilities. Now, what are the a posteriori probabilities? These are the 4 a posteriori probabilities. Okay, please remember. So here we have discussed about these 4 probabilities, conditional probabilities. They are called transitional probabilities. Okay, here, so these are 4 called a posteriori probabilities. What is the difference? Difference is, now here, so probability of m naught given x naught, which means probability that m naught is transmitted when x naught is received. So in the same way, you can define remaining 3 conditional probabilities. They are called as a posteriori probabilities. What they are called as a posteriori probabilities. Okay. Now here, so what is the logic? Here we have to take the decision. Okay. Simply, suppose here what we know. Here we know that x naught is received. Okay. The logic is, so here suppose you are at the receiver side. You know what is received, but you don't know what is transmitted. Okay. Suppose x naught is received. What might be the transmitted signal? It can be m naught or it can be m1. Okay. We don't know. You have to take the decision. So from the known quantity, we have to find out the unknown quantity. What is known quantity? You know what is received. You know something. You received something, but you don't know what is transmitted. Okay. Suppose if x naught is received, we have to find out what is transmitted, either m naught or m1. Okay, that is one scenario. Next scenario is you received x1, but you don't know what is transmitted. Either m naught is transmitted or m1 is transmitted. Okay, so from the known quantity, it's the receiver, you have to find out the unknown quantity. Okay, so but what do you know generally? You know, so this probability of m naught, probability of m1, and you know these 4 transitional probabilities. Okay, now, so that is nothing but decoding. Okay, you have to decode. You have to decode what is transmitted. Now, suppose here. So how to decode? That says that's given by map rule, maximum a posteriori probability. Okay, which means, so we are taking the maximum a posteriori probability. So if which one is having maximum a posteriori probability, we take decision in favor of that particular signal. Okay, so let me explain. Suppose if x naught is received. Okay, if x naught is received, so what are the two possible a posteriori probabilities? Okay, so the two a posteriori probabilities are probability that m naught given x naught, probability that m1 given x naught, which means probability that m naught is transmitted when x naught is received, otherwise probability that m1 is transmitted when x naught is received. These are two corresponding a posteriori probabilities when x naught is received. You know x naught, that is known quantity. You have received x naught, but you have to find out what is transmitted. Okay, what do we do generally? So we compare these two probabilities. What two probabilities? X naught is received now. So this one and this one. We compare this probability and this probability. Two a posteriori probabilities. We are comparing these two a posteriori probabilities. Okay. Suppose if this is maximum, what do you say? You say that m naught is transmitted. Suppose this is maximum, what do you say? You say that m1 is transmitted. That's it. Okay. So we are going for the maximum a posteriori probability. Okay. Why maximum a posteriori probability? Because this defines our decoding problem. Because so we don't know what is transmitted, but we know what is received. So we have to find out probability that m naught is transmitted given that x naught is received. We know already x naught is received, but we don't know what is transmitted. So in this scenario, we go for a posteriori probabilities. Okay. Now what would happen? Simple logic. If this is maximum, we say that m cap equal to m naught. If this is maximum, we say that m cap equal to m1. Okay. So by this diagram, just so suppose I have received x naught. I know this is known quantity. I don't know what is transmitted. What I do? I'll compare the two a posteriori probabilities. Suppose probability of m naught given x naught is maximum. I say that m naught is transmitted. Otherwise, I say that m1 is transmitted. I do same thing for x1 also. Okay. Now here, so the name itself indicates maximum a posteriori probability rule or simply map rule. So we have to choose which one is having the maximum a posteriori probability. Now we take the decision in favor of that particular symbol. Now reverse may happen. If x0, x1 is received, we compare these two a posteriori probabilities and we take the decision in favor of that particular symbol. Okay. Now, so I hope you're okay with this. Now, so how to find out these probabilities? Okay. How to find out these probabilities? Okay. We use Bayes rule. This is a Bayes rule. Okay. So I hope you are okay with this Bayes rule. So here in the denominator we have probability of B. So probability of B is this much. How to write this denominator? It is a total probability theorem. So you go to your PTSP course once and try to study them in detail. Okay. So here I don't want to explain each and every time, each and everything in detail now. I hope you are okay with this. Okay. Now my aim is to find out the posteriori probabilities, which I don't know. Okay. But what I know, you know these two things. You should very cleverly calculate. What I know a priori probabilities. Means what? I know what is P of m0, what is P of m1. I know transitional probabilities. I know P of x0 given m0, P of x0 given m1, P of x1 given m0, so on so. Okay. So by using these two, we have to find out a posteriori probabilities by using Bayes theorem. Okay. Now, so actually this is the map rule. Correct? But we don't know these two probabilities. Then what we do? Apply Bayes rule here. So P of m0 given x0 equal to P of m0 into P of x0 given m0 by P of x0. Simply, you know already, P of A given B. What do you write? P of A given B equal to, what do you write generally? Denominator P of B by P of B given A into P of A. I hope you are okay with this simple rule. You take pen and paper, try to write down everything in detail. Okay. So this is what I have used here. That is a Bayes rule. Now this is for P of m0 given x0. The same way, what is for P of m1 given x0? This is what you get using Bayes rule. Now I am replacing P of m0 given x0 with this term, P of m1 given x0 with this term. So here, so P of m0 given x0 is this term. Am I right or not? Just verify, please. So P of m1 given x0, this term. Are they same or not? Just try to find out. Yeah. So both are having same denominator, so they will cancel out. Now P of m0 into P of x0 given m0 greater than P of m1, P of x0 given m1. If it is so, we choose m cap equal to m0. Okay. Now if reverse happens, suppose this is more, what do you do? If this is more, what do you do? Choose m cap equal to m1. Reverse happens, m cap equal to m1. So let me verify once. You also verify if there are any mistakes. Yeah. So this is what finally we got the map rule. So because you know all this, you know P of m0, you know P of m1, you know P of x0 given m0, you know P of x0 given m1 also. They are given, they will be given to you. They are transition probabilities. They will give you P of x0 given m0, x1 given m0, all these four transition probabilities, and they will also give you a priori probabilities. What are they? P of m0, P of m1. Okay. Now, so this is what finally the rule is. This is finally the map rule. So this is optimum rule. Okay. Now, so this is how decoding will be done. So map rule means maximum a posteriori probability. Simply, so we receive some vector x. Okay, simple rule is we receive some vector x that is known to us. So what is unknown to us is what is transmitted. So we find out the all possible a priori probabilities. So suppose if the for suppose second a priori probability is more, what do? You take m cap equal to m2. Suppose fourth a priori probability is more, you take m cap equal to m4. Simple rule. Okay, here I have taken a simple form of binary channel. So this is the simplest form. So it will not be same always. I have taken simplest form for only for explanation purpose. All the techniques will not be like this. So to understand the basics of map rule and ML rule, I have taken this scenario. That's it. So don't expect that everything will be in the same fashion. No, just simplest form of the channel. Okay, two are transmitted, two are received. Okay, now, but remember, so we have to, at the receiver you have to find out the maximum a posteriori probabilities. If the fourth one is maximum, we say that m cap equal to m4. If the last one is maximum, we say m cap equal to mm. That's it. Okay. Now, so this is map rule. Now, what is the ML rule? That is maximum likelihood rule. So here, this is the special case of map rule. It is not a new rule. It is special or simplified version of map rule. Here, what we do here is, what we take here is, we say that the symbols are equiprobable. What symbols? P of m0 equal to P of m1 equal to 1 by 2. So the transmitted symbols are equiprobable. So we are transmitting two symbols. So the probability of which symbol will be 1 by 2. So then what happens? So P of m0 is same as P of m1. These will be cancelled because they are same. So this is simplified rule. That's it. Okay. Now then what happened? This is what you get. So it is called maximum likelihood rule. So this is what is the ML rule. This is what ML decoding. So if you go back to the basic diagram, there I have written ML decoding. ML stands for maximum likelihood decoding. So we always use maximum likelihood decoding. Why? Because I told you in the starting itself, we assume that all the M transmit symbols are equiprobable. So let me go back. I told you in the starting itself, that's why I need your complete attention. I don't know whether I have written here or not, but maybe not in this slide. In third unit I told you. So we assume that all the M transmit symbols are equiprobable, and so that each and every symbol will be transmitted with a probability of 1 by m. Okay, you go and see in third unit. I think it is there in third unit. Okay. Anyway, so that's why if the symbols are equiprobable, we go for the simplest form of map rule, that is called ML rule, maximum likelihood rule. What it says? It is something like this. So please remember, I have explained map rule and ML rule only for what case? This binary channel case. Okay, but so in practice that may not be the case always. But I hope you got the complete idea of the what is ML rule and what is the map rule. So ML rule is a special case of map rule whenever all the symbols are equiprobable. So you get ML rule. If they are not equiprobable, you have to go for map rule. That's it. But in our course, we have already assumed that all the symbols are equiprobable. So we always go with the ML rule, maximum likelihood rule. But here, what is the maximum likelihood? Again, you have to go for the maximum likelihood function. What is likelihood function? What is that? L of mi. Where is that? Yeah. We have to find out whichever is having maximum. I will be varied from 1 to m. I will find out all these values, m values. Suppose for I equal to it is maximum, we say that m equal to m2, second symbol. Suppose if it is for I equal to 4, it is maximum. Among m values, for I equal to 4, it is maximum. What do you say? M equal to m4. So that's it. Simple rule. Anyway, now, so I want to write the generalized version of map rule, ML rule, something like that. Now, these are the map rule, ML rule. What the map rule says? Set m cap equal to mi. Okay, what is happening here? I am comparing all a posteriori probabilities. This is a comparison. Please remember, k varies from 1 to m. Okay, see here, probability that mi is transmitted given that x is received. I am comparing x is common, x is received, we know that, but we don't know what is transmitted. So that's why I vary k from 1 to m. Okay, suppose what I do, it's just comparison. No, see, suppose I give you an array of 10 numbers. Okay, I'll give you an array of 10 numbers. So I want to find out which is the maximum. What do? You fix one quantity and compare with the remaining quantities. No, that is simple logic, right? So that's what we write code. Same thing. I am fixing mi. I am varying mk. Okay, k varies. Suppose mi is fixed, k is varying. Okay, it's just like finding the maximum number of maximum value of the given number of given array. Suppose array contains 10 values. We have to find out the maximum value. What do? You just compare. No, same thing like this. I am comparing which one is having most a posteriori probability, or which one is having maximum a posteriori probability. Okay, I hope you are okay with this at least, right? Now, so for this you can apply Bayes rule. What happens? So alternatively, by using Bayes rule, set m cap equal to mi. So p of mi given x is same as p of x given mi. So this becomes like this. So both are same. This is the direct form. This is by using some Bayes rule. Now what is ML rule? In ML rule, p of mi is same as p of mk, which means all symbols are equiparable. These two will be cancelled out. You are left with what? P of x given mi is more than p of x given mk. For all I is not equal to k, please remember, and k varies from 1 to m. Okay, or so instead of finding the probability, I am finding the maximum PDF. PDF resembles probability. So if probability is more, which means PDF should be more. So they have direct relation. So here, so instead of going for the probability, maximum probability, I am going for maximum PDF because I know this quantity. Just now I found out, isn't it? Now, so for k equal to I, okay, so I will find out for which one it is maximum. Okay, in simple sense. So without any confusion, I just say like this. Okay, so if you are getting any confusion, simply let me go to this f of x given mi or mk. Where is that? Yeah. So here, now suppose this is the conditional PDF of the x given mi. Okay, I varies from 1 to m. I'll get, if I vary I equal to 1 to m, I'll get m values, no? M conditional PDF values. Suppose for I equal to 4, it is maximum. The maximum value is occurring for I equal to 4. Okay, so this conditional PDF is maximum when I equal to 4, which means what? Fourth symbol is transmitted. Suppose if it is maximum for I equal to 10, 10th symbol is transmitted. That's it. Okay, that's a simple meaning. Correct? So that is ML rule. Nothing more than that. What is ML rule? Maximum likelihood rule. We are finding the maximum likelihood function. What is likelihood function? What is likelihood function? So that is a natural logarithm of this conditional PDF. Okay. So if PDF is maximum, natural logarithm of that PDF is also will be maximum. Okay. Now simply what is ML rule says is, what it says? So likelihood function should be maximum. What is likelihood function? This function should be maximum. That is a conclusion. Okay. So we will vary I equal to 1 to m. We find out for which value it is maximum. Suppose if it is maximum for I equal to 1, what do? You choose m cap equal to m1. Sorry. Okay. That's it. That is a decoding. So that is ML decoding. Okay. Now. So this table gives you the final ML rule, generalized ML rule. Okay. So we stop here. So you try to understand this carefully. Okay. Thank you.